We're going to move on into to our next session, which is one of my favorites. It's about space power and propulsion. This session is sponsored by the Aerospace Corporation, so we'd like to thank them again for their participation in the symposium and their sponsorships. Again, this session will be talking about power and prop. Our moderator this year for this session is Stephen Edwards. Stephen's the Marshall's mission architect, so he'll be leading us on this effort. Stephen, take it away.
Thanks. So I'm the mission architect in the Advanced Concepts Office at Marshall. I'm nothing so grand as the mission architect for Marshall. But I'm excited to moderate this panel. Power and propulsion technologies and the missions that make use of them are things that we work on and I work on every day. So I'm looking forward to hearing from our panelists. I actually took the liberty during the break of rearranging the seating so that we actually go in order and that I think we're going to present in. And so I'll go ahead and introduce briefly our panelists, and they're going to each give about 10 minutes. They can probably go a little bit over, but I probably shouldn't have said that. And then that should, in theory, give around 20 minutes for discussion afterwards. So hoping for some good questions and discussion. So first I have Vince Bilardo. He currently serves as the Senior Executive Program Director, overseeing all aspects of Maxar's PPE program. And I'll add, in a previous life, he worked for over 30 years with NASA here at Glenn Research Center. So I don't think it was called Glenn, but that's right. Next up will be Andy Hoskins, who has worked at Aerojet Rocketdyne for more than 32 years in a range of roles, from research to project management to business development and government relations. His specialty is in electric propulsion, but he'll be covering the gamut of what Aerojet Rocketdyne does in his time this morning. Next, we have Dr. Christine Edwards. She is the Deputy Exploration Architect and an Associate Fellow at Lockheed Martin Space. She co-leads the Commercial Civil Space Advanced Programs team in architecture and technology development for future human spaceflight missions. And then finally, our anchor for the panel, Dr. Kelsa Palomares, is Nuclear System Engineering Manager at AMA, where she supports NASA's Space Nuclear Propulsion Project. She has a background in design, testing, and experimental investigation of new and novel concepts for space reactor development through materials and hardware development efforts at both NASA and Department of Energy. So with that, I'll give it to Vince to lead us off.
Okay, good morning, everyone. And before I get started, let me just say that how nice it is to be at my alma mater. I actually got my aerospace and mechanical engineering degrees here back in the day. I won't tell you when, but let's just say it was back in the day. And it's great to see some of the students and young people, early career people here attending this conference, because you all are the future. And hopefully we'll be able to show you a few glimpses of what we think that future might hold here on this panel. All right, let me see if the clicker works. Great. So kind of beyond the tech starts with, well, where is the tech today? What is the current state of the art of both power and electric propulsion as of today? And so this chart is one we put together at Maxar that tries to kind of visually show the roadmap that Maxar is attempting to implement for high power electric propulsion. And you can see that there are kind of three generations here. And when we say power and propulsion, it's really three domains or swim lanes that you can see on this chart. The solar array, because we're talking about electric propulsion, not quite talking about nuclear, but we'll get there here this morning. And so it's generating bus power from the sun. using solar array technology that, of course, has been used in space for many, many years, but that doesn't mean it's a completely mature technology yet. And so part of what we're trying to do at Maxar, working in partnership with NASA and NASA Glenn Research Center, which holds the power and propulsion element contract with Maxar, is mature the solar array technology to an unprecedented level using the rollout solar array technology from Redwire DSS, which will be the largest pair of solar arrays flown in space other than what is currently flying on the International Space Station. They will generate 62 kilowatts beginning of life power into the spacecraft bus, which again will be unprecedented for any spacecraft that is yet flown in space other than the ISS. Secondly, you've got to be able to process that bus power in a way that makes it suitable to power an electric propulsion Hall effect thruster. And so that requires a PPU, power processing unit. And you can see here 3 generations of PPUs that we have flown at Maxar, currently flying on our spacecraft at the 1.5 kilowatt 300 volt level, as well as a 4.5 kilowatt 300 volt level. Where we want to take this technology on the PPE is to a 600 volt operation, actually a switchable 600 volt operation. Obviously, the higher in voltage that you're going, the more efficient you can run the Hall effect thruster. And going from both 6 and all the way up to 12 kilowatt. We'll talk about that here as we show you the 12 kilowatt advanced electric propulsion system thruster that Aerojet Rocketdyne is providing for PPE here on the next 2 slides. Well, and that's a good segue into the Hall effect thrusters. So let me move on to the next chart. So this past quarter at NASA Glenn's Vacuum Facility 6 chamber, a very large world-class chamber on the Lewis Field campus, we had the first light. We're powering the 12 kilowatt AEPS thruster with our 12 kilowatt, or what we call our PPU 12,000 power processing unit. This was a very key test in bringing those 2 pieces of hardware together from 2 different companies and showing that they're working very well in the VF6 chamber. We did this integrated end-to-end hot fire test for a period of over 3 months earlier this year, and operated it at both, across actually an entire throttleable range from 3 kilowatts, 300 volts, all the way up to full power at 12 kilowatts and 600 volts. So a very key accomplishment in the development of the PPE here for NASA. And I'm going to try to show you the actual hot fire of the thruster, the lighting of the thruster here in the chamber. Give it just a minute. I know the suspense is killing you. No, I'm sorry. So, yeah, Mark, could you give me a hand there, back there, and oops, click on the image. Hopefully it'll fire. There we go. So that's in the electric propulsion world. That's kind of the equivalent of smoke and fire that the Marshall guys like to show at these things. But that's it. It starts really fast in milliseconds, and it's off and running. Okay, and let me just wrap up my remarks here this morning by kind of showing you a roadmap. So the theme of this panel is Beyond the Tech. So we're showing you what's flying in space today, what will be flying in space in just a couple years here on the PPE. But where do we go after that? We're all, I think, here to talk about, we go to nuclear. And nuclear, as it is currently being formulated, is really in 3 swim lanes: nuclear thermal propulsion, nuclear electric propulsion, and fission surface power to provide power to the electric grids that we will need at the Artemis base camp and ultimately in our settlement of Mars. And so you can see kind of a flow here of how the technology is potentially progressing from 1 kilowatt, kind of the kilopower level that's been studied and has been a NASA program of record that resulted in the Krusty experiment 4 years ago, very successful hot fire of a novel reactor at the Nevada test site, which has a great off-ramp to deep space science. And as we flow from left to right, you're getting from 1 to 10 kilowatts, 10 to 100 kilowatts, and ultimately to the megawatt level, megawatt class and higher, once we are creating these settlements on the surface of the Moon and Mars, as well as transporting both crew and cargo to Mars. And so with that, I'll finish my remarks and pass it on to Andy. Thank you.
Hey, so I'm Andy Hoskins, and just a couple more things about my background. I spent about 20 years out in our Redmond, Washington facility working in space propulsion, and most specifically in electric propulsion. So electric propulsion is kind of my happy place, so it's great that Vince has sort of teed this up for me. But I'm going to cover the wide range of things that Aerojet Rocketdyne is doing in exploration, power, and propulsion. So about 12 years ago, I moved out to our Washington, D.C. office, the other Washington, and I have sort of a broader portfolio of things, but I continue to do a lot of stuff with electric propulsion. In fact, I was over watching the AEPS thruster fire yesterday. I'm not sure if it was with the PPU or not, but it was good. So I got a chance to see it in person. So that's for the first time too. It's great to be out of COVID. So Aerojet Rocketdyne, when we talked about power and propulsion, we do just a huge range of stuff to support the mission here, and we're really we're really honored and happy to be, able to, and I'm honored and happy to be working for a company that's able to work on such a wide range of things. From launch, I'll say a couple more words about, we build the RS-25 engines, the RL-10 engines for SLS, a bunch of the engines on Orion, I believe 22 of the thrusters that are on Orion. We've already touched on the AEPS, a couple more things I'll say, when I get to that there. And then we also work on space nuclear power, both radioisotope. So we build the RTGs for example, that are on Mars Curiosity and Perseverance, and will be on Dragonfly, as well as we've got one of the programs for the fission surface power. And then on space nuclear propulsion, we actually, with the combination of Aerojet and Rocketdyne, we actually have history in both nuclear thermal propulsion and nuclear electric propulsion. So some work there, on that, looking towards going forward and what's the roadmap there. And then actually on top of that, to sort of help us guide what we do a lot of architecture studies that involve trajectory analysis and like I said, architecture studies, so I'll just touch on some of these things. I just am going to kind of whip through these things, and hopefully this generates some conversation, as we go along. So on SLS, as I already mentioned, we build the RS-25 engines. Those are Space Shuttle main engines, and the engines that are going to go on Artemis 1 have already actually flown on the Space Shuttle. But I think after after Artemis 3 or Artemis 4, we get into new engines that are slightly upgraded with a little bit more power, a little bit more thrust. The RL-10 engine on Block 1 up to Artemis 3, there's a single RL-10, and then when we get to the exploration upper stage, there'll be 4 engines on that. On Orion, as I mentioned already, there's 22 engines that are done on a range of different things, from the launch abort system motors to engines that are on the crew module, and also the main module, the main engines. These are all, except for the launch abort system, these are all built in Redmond, Washington, in our in-space propulsion area. One of the things we talked about a little bit was, sort of a theme for this was as we evolve things, what are the challenges there? And I sort of got thinking about that relative to, SLS and, the evolution. This is an evolution, for the SLS up to, this is actually out of the guidebook, the NASA guidebook for SLS. But as we go along, SLS, once we launch here, hopefully in the next 2 months, sometime in the next 2 months, SLS is going to provide unparalleled payload capability to lunar orbit and future Mars missions in terms of what's able to go, translunar and ultimately able to go. But the challenge as we scale up for all this increased capability is going to be to control costs, and we're very focused on that. So we're looking at things like, is there a commercial service model ultimately that will lower cost and increase launch frequency? So these are a couple of things that we're looking at there. Back on the AEPS Hall thruster system, Vince already covered a fair amount about this. This is a 12 kilowatt system. We've already gone through engineering test unit tests at JPL and GRC. So we're basically at TRL6. We went through CDR in March, and we're in the process right now of building flight units. I believe there's 2 qual units that are being built, one which is going through environmental tests, and then the other is going through more life tests as we go along. And actually, one of the challenges here is that the life for all these things is very long. I believe the life is something like 25,000 hours. We're obviously not going to test that before we get to launch. So we're going to be testing while we're in the process of integrating and going through launch. But these are all on track to be delivered to Maxar in time for launch schedule. I think by the end of 2024 is the current schedule right now. One of the things I also wanted to talk about, again, in terms of progression, and Vince sort of hit on this, and this is sort of an expanded version of this. If you look at the second lowest one, the first flight unit of Hall thrusters was actually, Hall thrusters were, and this is just one form of electric propulsion, by the way. There are multiple forms, but I'm just picking on this one because it kind of ties in with what's going on here. One of the things that's going on here at NASA Glenn. But the first Hall thrusters that were flown were actually flown by the Russians, by the Soviet Union. We didn't realize that they were flying them until the Soviet Union opened up in the early 1990s. And the first flight of a 1.3 kilowatt Russian Hall thruster was in 1994. There were actually smaller ones flown somewhat before that. But this was the first, sort of commercial version. And at that point, what people looked at was just station keeping for geosynchronous satellites. The next evolution was a series of ones that were in the sort of 3 to 5 kilowatt range. They're just examples here. SPT-140 is a Russian version of it. PPS-5000, there's a Busek version that hasn't flown yet, but is actually on the PPE, and Aerojet's XR5. This allowed people to move to orbit raising. Then you move up. So this just shows where AEPS is in the middle of this. This is the next evolution up. And at 12, 13 kilowatt kind of level. And this ends up being more for, you start to look towards logistics, early Mars cargo, things like that. We've done tests at up to 100 kilowatt level thruster, but one might sort of wonder, should there be a step in there in 30 to 40 kilowatt level? The University of Michigan has tested this a little bit. And then people have even talked about up to megawatt class, Hall thrusters. And these all end up needing to have nested rings. You can see multiple rings that are there, because if you just size the Hall thruster, it becomes an enormous racetrack, and the diameter gets to be very, very large for physics reasons, which I can go into at a coffee break if you want to. When we start to talk about getting to those levels, we also start talking about switching over to maybe another technology like MPDs. But these would be supporting things like NEP vehicles. At some point, you get to be too large for something that's solar electric, even with modern high efficiency solar arrays. So that just gives sort of a little bit of a trend. But the other thing that goes on in terms of challenges as you get to these things is how do you test something like this? So what NASA has started is what they refer to as a Space Technology Research Institute, and this one is called JANUS, after the god with two faces, and they're showing a Hall thruster and a gridded ion engine there. This is a collaboration of 11 universities, a lot of NASA input, and then also there's several folks who are on the Industrial Advisory Board, and the goal here is to establish ways of extrapolating from ground test type things, which have its limitations. And those limitations become more and more severe as you go to power levels at AEPS or even higher. And so they have three research thrusts, which are facility effects, diagnostic development, and model and simulation. This is, I think, a very important thing toward going towards how do we get to that future level. Okay, so another area that we work on is space nuclear power, and there's also evolution going on here. There's radioisotope systems. MMRTGs are being used right now, and the goal on all of these is to increase the efficiency. There's pros and cons. I'm not going to get into them right here for time reasons, but basically you're trying to move towards higher level things. With radioisotope, you don't have an active fission reactor. You're just watching something like a plutonium isotope or other isotopes decay and picking up the heat on that. But to get to significantly higher efficiencies, you can see the efficiencies are very low for thermoelectric. You need to go to a dynamic thing. And so this is a recently awarded program called DRPS for Dynamic Radioisotope Power System. To go to levels that we need to go for power to actually go out and explore, we need to get to fission systems. And that's where we talk about things like going from crusty. There was a kilopower program in around the 2018 timeframe. And now more recently, there's the start of the fission surface power, 40 kilowatts. But ultimately, when you're talking about Mars, you're talking about megawatt type things to do useful things. And the challenges there are going to be, how do you land this? How many different components are there going to be? How do you break this up? How do you network it together? So other things to sort of potentially talk about. Vince touched on NTP and NEP. We're looking towards that, in terms of, do we start this right now? I think that what NASA's approach is to start with fission surface power and get working on that, and then get going on components for NEP and NTP. The challenge is that there have been National Academies studies, for example, and internal NASA studies. But the main challenges for NTP are materials and how do you test this? We can't test like we did in the 60s on the ground as easily. And so there's challenges there. For nuclear electric, the challenges there are you have very large radiators. So for a nuclear electric, if you have 25% efficiency and you have a 2 megawatt power system, that means you're going to have to fly something that's going to dissipate 6 megawatts of thermal energy. So that's a huge thing. Second piece of this is, how do you integrate all this stuff? And how much of the integration do you do? So this just kind of shows some of the functional comparison between these, and we take a look at all these things as we go through and do various architecture studies. We do a lot of work on both types of things. On this, I just wanted to give you an example of what we're looking at in terms of the functional comparison between the two systems. And then finally, like I said, architecture trades. And the goal here is to understand the system level issues, including the different trajectory options and how this factors in with all the different subsystems. This gets to be a fairly complex sort of a thing. We trade the impacts of the subsystems on the overall score. And we use this to guide the development of the subsystems with these trades. The key thing here is to look at overall mission success metrics and not just individual element performance. And I'm going to let it go at that and pass it on to Christine.
All right.
Oh, sorry, you have a thing. Yes.
All right. Great. So today I want to talk about how lunar infrastructure for power can build up over the next 5 to 10 years, and then extrapolate from there into the future to the next 30 years and think about what could that infrastructure enable going into the future. So this is a slide that I presented last year at the Glenn Symposium. So it shows several phases of buildup of lunar infrastructure with the early Artemis missions. The first phase is a mobile architecture that would be built up during the initial few missions where we're going to several locations around the lunar South Pole region. And the infrastructure can be mobile so that it can move from one site to the next to support those landed missions. So this infrastructure can include the lunar mobility vehicle, a pressurized rover, and the vertical solar array technology to provide additional power using the Parsec satellites for communication relays. And then when a base site is selected later on, then that infrastructure can be integrated into that base site, adapted to become part of that lunar Artemis base. And so the VSATs can be placed at locations that provide great illumination to feed power down to microgrid hubs that can power habitats and ISRU, in situ resource utilization elements. And a fission surface power elements can provide nuclear energy that's steady through the lunar night and has higher power levels that can help feed those ISRU demonstrations and habitat power needs. And then as new technology is developed and matured, it can be incorporated into this lunar architecture, including power beaming, like power beaming into craters to assist with ISRU. So overall, these elements all build up to a foundation for a more sustainable future in space. And so you had talked about how your happy place is electrical propulsion. So my happy place is sustainability and resilience, and in particular developing system architectures and data science that enable sustainability and resilience. And so when I talk about that we're laying a foundation for a resilient future and for a sustainable future, I'm talking about three different ideas for sustainability. The first one is enabling a sustained presence of human and robotic exploration on the moon. And then doing demonstrations of ISRU so that we can enable better usage of resources or local uses of resources. So that's enabling better resource sustainability. And then beyond that, that activity being a catalyst for a lunar economy. So then we are enabling better economic sustainability. So now that we've set that foundation of what the next 5 to 10 years could look like, I want to peer even further into the future, looking at what could space 2050 look like. And so at Lockheed Martin over the last couple years, we've been doing an exercise. We're trying to think about what would space 2050 look like, and it's to help us envision that future so we can plan our innovations to try and enable that future. And this is a future that may or may not happen, but it's fun to think of what could be to help drive what we're doing now. What we're finding when we're doing these analyses of the lunar infrastructure, and just in particular ISRU and ISAM, is that we're finding that the activities that we're going to do on the moon are going to be limited by the power that's available on the moon. But if we build up these capabilities so that they're modular and scalable, if they're interoperable and interconnected, then as we deliver more infrastructure to the moon, as we connect it and operate it, the power capabilities can grow over time so that we can create on the moon a power infrastructure that could be very similar to Earth, but different. And like, for example, this infrastructure can include power beaming, which is illustrated here in this picture, this futuristic image. So we have a power beaming concept in the lower left that has a nuclear power plant inside that dome. It's feeding energy into the laser transmitters that are beaming power to other elements on the lunar surface. And at Lockheed Martin, one of the technologies that we're developing is laser transmitter technology to try and enable this kind of future. up in orbits, we have more power beaming and also a propellant depot. So as power becomes more available on the lunar surface, we can use that power to mine the materials out of the moon to create propellants. And propellants can be transported up to a propellant depot in orbit. This propellant depot could provide propellants to landers, other orbital elements, and to a Mars transit vehicle. So this is the Mars Transit Vehicle concept that we've been developing over the past year at Lockheed Martin. It's called Mars Base Camp, and this particular configuration that we've been developing recently is Mars Base Camp that incorporates nuclear thermal propulsion. So this Mars Base Camp would be fueled starting with Earth-sourced propellants, and then transition to lunar-sourced propellants as ISRU is set up. And so the mission's design is that it's assembled and fueled at the gateway. It transports crew from the gateway to Mars, and then it stays in Mars orbit for a month to a year while the crew does science investigations on board. Inside that, the science laboratories on Mars Base Camp, they can do sortie missions down to the Mars surface and landers like the one shown. And they can do sortie missions to the Mars moons using the Orion and one of the nuclear propulsion stages. After the mission is done, it returns them to the gateway, and then they return to Earth on the Orion. So what we found in our studies here is that the nuclear thermal propulsion has such high thrust and high capability that we're able to do various kinds of Mars missions with 2 to 4 of those centralized golden tanks. So it's very capable to be able to do various kinds of missions. And this year we've been investigating what kind of abort scenarios and fast transit missions can we do with nuclear thermal propulsion. So the capabilities that we're developing for the moon can apply to Mars as well. For example, the fission surface power can be very enabling on Mars because of the lunar dust storm. So what we found is that solar array technology on the Mars surface gradually gets diminished, gets covered up by the dust storms, by dust. So what we think that could really enable Mars missions is fission surface power, which would not be as affected by the dust. And advancements that we make in space can apply back here on Earth. So what we are trying to envision on the moon and Mars are these very interconnected systems that they're built up of these modular pieces that all work together. You're sharing power, you're sharing data, and there's autonomous robotics that are servicing and doing various activities amongst all these systems. And so this infrastructure that we want to build on the moon and Mars is almost like building smart cities on the moon and Mars. But so they can be very Earth-like. Like I said before, they can be very Earth-like, but different. So here I'm thinking about how they could be very data-rich, where we have a lot of data that we incorporate into our space systems right now. We put on a bunch of sensors on our systems. We make them telemetered, so we get lots of data down. And by getting all that data, we can optimize how we operate and use these systems in space. And so if we're starting to create these like smart systems in space, these smart cities, we can learn how to better operate the power and infrastructure in space and apply those lessons learned to Earth. Like, for example, I have an example of the other way. At Lockheed Martin, we're using some data analytics approaches for monitoring the safety of nuclear power plants. And we're trying to apply those to our spacecraft for monitoring the safety of our spacecraft. So, and as we've seen in this history of space exploration, the developments that we do in space help improve the way things we do on Earth. So I think that as we move forward into this future, that we will be making life better in space and on Earth.
Well, first, I would like to start off with acknowledging what an exciting time it is to be a part of this industry. You've heard already today about the innovations that are actually happening right now, which I know we put a lot of time and effort to make these demonstrations succeed, and then the possible futures going forward, which I hope we're a part of making a reality. And then especially for the students out there, I think now is an awesome time if you're excited about these technologies to get involved. There's a lot of opportunities right now. When I think about moving beyond our current technologies and advancing towards future missions and future mission needs, I really think that nuclear has to be a key part of that story, as we've heard from everyone else today, whether that be fission or radioisotopes. But one standout example of nuclear being a part of that story is space nuclear propulsion. So we've heard about some of the benefits and some of the missions we can enable with space nuclear propulsion technologies. Fission compared to radioisotopes, solar power, chemical power has the possibility for the highest power density per unit mass. So we heard about designers saying they think about mass, mass, mass. So fission can get you there. And it also really thrives in providing high power levels for long periods of time. So those attributes together can either enable more complex missions or add increased capability and robustness to our baseline missions. We've heard today that there's two major options for in-space propulsion, especially for going crewed missions to Mars, and they are nuclear electric propulsion, NEP, and nuclear thermal propulsion, NTP. And the reactor is really the heart of these technologies, but is also one of the key challenges in enabling these technologies. But luckily for us, we're not starting from scratch. There have been heritage programs, many legacy programs within the US that give us a firm foundation. Whether it be these programs have by and large demonstrated the feasibility of these systems. We know they can work. We just need to develop the technologies to get us to the performance we want. And we can use the historic testing and design and component demonstration data as a foundation to get there. But I do acknowledge there are new challenges for our current missions under consideration. We require higher performance than what has been demonstrated through these historic programs, or even what was set as the design goals for some of those historic programs. And there's new policy that both opens the door in enabling operations and implementations of these systems, but it also restricts us in our use of enrichment. So copying and pasting historic solutions for reactor technologies just really doesn't cut it for getting us to where we want to go. So I just want to talk real quickly on some of the specific challenges for both NEP and NTP for reactor technologies. So current, as you've heard, current reference missions that are being considered for nuclear electric propulsion require a hybrid nuclear electric propulsion chemical system that's megawatt class. So reactor development needs for this system are to enable high performance, meaning high efficiency, and sustainable, reliable power. So looking at megawatt level reactor technologies that operate at high temperatures so they can be coupled to a high performance power conversion system. When we look at our heritage and our current technologies, such as the SNAP system that was developed in the 50s and 60s, that system that we demonstrated in space was only capable of less than a kilowatt electric power level and less than 2% efficiency. So we have a long way to go. But luckily for us, reactor technology hasn't stagnated since SNAP. There's been a lot of advanced reactor technology development within the US and internationally. And actually, a lot of that development has good overlap with the design needs for nuclear electric propulsion. So there are differences. The operating environment can be higher temperature. We need to be a low mass system to be competitive and high performing. So optimizing the system for mass in a space application is really key. So for here, we want to leverage existing technologies that's been developed and demonstrate these components under NEP operating conditions. We also need to demonstrate reactor operations and controls. You talked about instrumentation and making sure we have a reliable system. We need to make sure that any reactor that we put in space is safe and reliable. So we will need targeted testing to demonstrate reactor operations and controls. And then thinking about rolling up the reactor into the system level, we're thinking about sizing of the reactor, making sure that we can get everything in space, and then making sure that the reactor is capable of meeting the requirements for in-space assembly and manufacture. For nuclear thermal propulsion, the system operates a lot differently than typical reactors. We're not coupling the reactor as a heat source to a power conversion system to generate electricity. In this case, we're directly heating our propellant. So key here is to make the reactor as hot as possible so we can get as high performance as possible in terms of specific impulse. NTP reactors have been extensively tested and demonstrated. There are over 20 reactors demonstrated in the US rover NERVA program between the 1950s and early 1970s. These tests demonstrate reactors that were capable of thrust levels between 15,000 to 250,000 pounds force thrust. However, the specific impulse of these systems were only limited to 825 to 850 seconds. Today, we want to at least get to about twice that of the best performing chemical engines, so 900 seconds or greater to meet current crewed missions. So we see here there's a breakpoint between what we've demonstrated as our technologies for high performance fuels, which enable high specific impulse, and where we need to go with even higher performance. So we need materials innovation for the fuel forms, and then this system, very different than traditional reactors. So demonstration of integrated reactor engine operations and the facilities to enable us to do that are really key to this technology. And then looking forward in making sure all the pieces come together on the system level, we can't take our eye off the ball for cryogenic fluid management, especially for large CFM loads. So all in all, we have history and we have challenges. New development is needed to make these systems a reality. I think it's going to be a national effort by both national labs, the NASA centers, the new pipeline, academia, and then obviously industry is going to play a key part of that. But once we are successful, it will truly be a national achievement. So thank you.
All right, thank you very much. That was a great opening salvo. I actually do not have a good read on time. I did not take a good note of when we're at, so I'll just wait for someone to start waving at me or whatever when we're wrapping up. So we will be asking, or I guess opening up for questions or discussion topics from the audience. But I wanted to lead off, and I kind of had queued the panel for this ahead of time, and I think you kind of talked about it some in your presentations. But obviously, for me, working in the Advanced Concepts Office, we're looking at future missions, human and science, and all forms of exploration. And generally speaking, it's always a push. No matter what the scale or what the mission is, there's a push for more, right? More power, more thrust, longer lifetimes, more reliability, more autonomy. Of course we want more, right? So I guess, there were a few places that we were called out, but so you can re-emphasize those or just draw particular attention to. Obviously, going for more means scaling up from where we're at. It means advancing beyond what we've achieved, and there's always challenges that we encounter when that happens. So I guess, opening out to the full spectrum of all different functions that fall into propulsion and power, where do you all see some of those challenges, or maybe are experiencing current challenges. And challenges are not bad. They're there to be overcome, and it's a big, that's where our success doesn't come without a challenge. So, anyways, just and in whichever order, it looks like Christine, you're ready.
I'm
to
ready.
Go.
So I'd like to talk about, a couple of challenges that I've seen. They're actually more like traditional challenges that you see with spacecraft, because I was in mission operations for the Grail and Juno missions, and had power challenges with both of those, where for Grail, whenever we wanted to extend its mission, we had to fly through an eclipse of the Earth over the moon, the Earth shadow over the moon, and it was the longest eclipse that we had to live through, and it was our spacecraft wasn't designed for it. So it was very challenging to try and make sure we would survive that. And now we're talking on the moon of longer night periods, trying to have our systems survive 4-day nights, even longer ones at the equator. And then Juno was the first spacecraft to go into the outer planets using solar panels. And so I was on the launch team for that, and dealt with like some of the power issues that we were trying to design into that spacecraft as well. So you were right. More power is something that we always would like to have. Higher power, but lower mass, right? So, so I just wanted to give some historical perspective of and stories behind your statements of that we do like more power, or power is a challenge in these space environments.
I think, you ask a sort of very general question of a lot of different technologies, a lot of different time scales and things like that. But I think one thing that sort of unifies things together is the challenge of people and expertise, and where that resides and how to retain it. Sometimes some of these projects are, career-wise long, or multiple career. I sometimes say this is like medieval cathedral building. It may be multi-generational. So you have to train your kids, or we need to be thinking about how we bring people along while things are being developed slowly. I think NASA is an amazing repository of a tremendous amount of capability, and we're not doing this alone by any stretch. In fact, it's really NASA is leading in so many of these things that are so far beyond. But we have to be thinking about how we go forward with sort of succession plans and so forth at levels that are sometimes difficult. On the nuclear propulsion, it's not clear what our funding levels are going to be for the next 5 years, and many people are starting to get to retire, both in industry, academia, and at NASA.
I'll add one more piece. When you decompose these technologies, whichever of the three nuclear swim lanes you're talking about, fundamentally you get down to a materials problem. And so what we need is more advanced materials science, more research at the fundamental level, and then taking those potential new materials through the TRL Valley of Death so we can deploy them and get to those 2,000 degree Kelvin temperatures inside the NTP reactor, right? What do you have today that can actually handle that? So we need more materials research.
I completely second that. As we try to move towards more advanced performance, nuclear thermal propulsion and nuclear electric propulsion systems, we're pushing to higher operating temperatures than what's been demonstrated. And oftentimes, we're exceeding materials breakpoints beyond that which we have currently developed. So we need to start from anew. I think there also could be a benefit from some strategy on how we demonstrate with current materials that we know this is going to work and start to build up that knowledge base instead of waiting for that next future material. Although it is important and enabling, we need to get experience with our current professionals now.
All right. Well, I see a first question from the audience lined up, so I'll.
Yeah, I wondered if you would address two areas that I did not see or heard in discussion. One in propulsion, one in power. On the propulsion side, I think the Vasmir engine and where that fits strategically in that chain. At one time with Gerst, it was looked at as a test bed on station to possible reboost. And then on the power side, Jim Green had talked a long time about the Stirling engine, and I didn't see that mentioned at all up here as kind of a stopgap. And has that fallen off the table? It's not in the roadmap. So those two areas. Thank you.
Well, Andy, you had MPD on one of your charts, so maybe you can talk to that. Let me just address Stirling a little bit. Stirling is absolutely integral to what you're looking here for both, well, for fission surface power and potentially for NEP. So you need that dynamic power conversion piece to take the heat out of the reactor and turn it into electricity. You also need it in the RPS, and you had DRPS also on your chart. So Stirling is absolutely part of it and will indeed fly in these systems going forward.
Yeah, and I'll just say, I think that the DRPS concepts involve Stirling, for sure. So there's that. As we go up, we start to get to talking about Brayton cycles. There's cutoffs and things like that. Relative to Vasmir, I was covering I was the mile wide and an inch deep kind of a thing. So I showed that progression, for example, for Hall effect thrusters. If I was to show a map of EP technologies overall, we've done things where we've scaled up gridded ion engines and so forth. Those get to be sort of large at a certain power level. For Vasmir, it actually struggles to be efficient below a power level of about 100 or a couple hundred kilowatts. So Vasmir might be something which would be potential component when you're talking about the very high power level type things. But all these things still need to be sort of tested out and so forth. Yeah.
And I'd like to say when we're thinking about Vasmir that when I was in college at MIT, I went to a talk by Dr. Franklin Cheng Diaz, and the Vasmir was one of the things that really inspired me to pursue an aerospace career. So it's something that's very near and dear to my heart, that technology. And yes, a higher power future system that could be very enabling.
A lot of times for electric propulsion, our problem is power. We need someone to invent dilithium crystals, so that we have lots and lots of power at low masses.
All right, I think that's good.
Yeah, I guess if there aren't any other questions, I'd like to thank Stephen, Vince, Andy, Christine, and Kelsa for their time today and the great session here. So give them a round of applause, please.